Talk about the solution to this binary counting printing. So if you see the pattern in binary counting, the pattern is, let's forget 0 for now. Let's start with 1. After 1, what is the next number that comes in binary counting? 1 0. That means 1 is producing 1 0 by, you can say, multiplying it by 10. What is the next number? So that can be obtained 1 into 10 plus 1. Now this is first number, this is second, this is third. How do we get the fourth number? 100. So we are multiplying this with 10. Fifth number, so multiply this with 10 and add 1. Now sixth number, 110. Seventh number, 111. Now the point is, since we are going back and multiplying, we are leaving the latest. So what we do, we say let's start with 1. Okay, not the stack. So let's start with 1 and put that in the queue. In the beginning of our function, we put 1 in the queue, right? So first line will be declaring the queue and second line will be push 1. Now what we do, we write a while loop on the queue, and from the queue what we will do, we will start taking the number out. From queue, let's take this out. Once we get 1 out, what we should do, we should print the 1. So first number is printed, and what we should do, we should enqueue 2 more numbers by multiplying it with 10 and multiply 10 and add 1. So these 2 numbers are enqueued, 1 is gone. This is what queue looks like right now. We have enqueued 2 because we know next number that we are going to get should be obtained by multiplying this by 10, right? So then what we do, we take this 10 out, we print it here, and we enqueue 100 and 101. So queue is serving the purpose that whatever we have to process is still in the beginning of the queue. So 10 will be printed, then we take 11 out, we print 11 and enqueue 110 and 111. So this way we can go as long as we are not done with how many numbers we wanted to print. And we have to print n numbers, right? Here the challenge was we want to include 0 also. So if 0 is there, we need a special handling for that, right? So if we quickly discuss the solution here, first thing we need is queue of int. It's a queue. Next, what we do? Print 0 directly. But what if n is 0? Then it's a challenge, right? But we can check. If n is greater than 0, what we do? Printf 0 space, that's it, right? After that, we can do n minus minus, right? Now, we should say q dot push of 1. And here, after n minus minus, if n becomes 0, we don't want to proceed further. Return simply, correct? So that case handled. Now we have pushed 1 in the queue. What is the thing that we said we will do next? While not q dot empty, what do we want to do? Pop the first element. How do we get the first element? Front. Because in stack the function was top, here the function is front. So we say printf %d q dot front. This will give us the first element. Then we have to push after multiplying this. So we say int x is equal to q dot front because we need x. We print x, and what we do, we say q dot push x into 10 and q dot push x into 10 plus 1. These two things we push and we keep on going. Now the question comes, when will the queue become empty? Because every time we are taking an element out, we are printing and we are adding 2 more. Or when should our loop break?
When n becomes 0.
N will, yeah, so n will become 0 only if we are subtracting it. So after every print, here if we have printed, if we keep on doing n minus minus, then we can put a condition while q is not empty and n not equal to 0. So the moment n becomes 0, we will come out of the loop and we will return. So this should work. Yeah, we have to pop the element because front will just give us the front value, it will not remove it from the queue. So we say q dot pop, this will remove. So let's trace it with an example. We'll take one or two examples. If n is 2, if n is 0, if n is 1, whether it is giving us the right output or not. If n is 0, n greater than 0, not true. It will not print 0. So there is a mistake here. Because when n was 0, we wanted to print. Oh, we did not want to print, sorry. We did not want to print in that case. So n0, this condition is not true. N minus minus happens. If n is 0, n is not 0, it will not return. So we should handle that separately. If n is 0, this n minus minus we can put after this. Now if n is 0, it will return immediately. Okay. So if n is 1, what will happen? N is greater than 0, true. We come here, n is not 0. We come here, we push 1 into the queue. But before that we have subtracted n minus minus. So n has become 0 now. We have pushed 1 in the queue. Queue is not empty but n is 0. Another bug, another issue, right? So what should we do?
If n is 1, we have to print just 0.
If n is 1?
Just 0 we have to print.
Yeah. So 0 would have been printed here. If n is 1, this will anyways print. Okay. And then n will become 0. If 1, this 0 is printed, that will happen. N is not 0 right now. We do n minus minus. We push 1. Q is not empty, but n will be 0. We don't enter the while loop. We don't need to enter the while loop. Yeah. So we have printed 0 anyways. So that case is done. So now let's trace the case of n is equal to 3. Rather than 2, we will take 3. If n is 3, this condition is true. Yes. We will print 0 first. Then we are checking n is 0, which is not true. N minus minus we do. So n is made 2 now. We are pushing to the queue the first element 1. Then what we do, we check queue is not empty, n is not 0 because n is 2. We go inside, we get the front of the queue which is 1 and we print 1. So after 0, 1 is printed. Then we are doing pop, so 1 is popped. Then we are pushing two things and n we are making 1. So n minus minus is also happening and we will push two things which is 10 and 11. Okay. After pushing this, we go up, q is not empty, n is not 0. We go inside, we pop the next element, we take the next element, front, which is 10, 10 we print, next we pop 10, n minus minus n becomes 0. We push two more things, 100 and 101. After that, if we come on top, n would have become 0. So we come out by printing 3 numbers. So this should work. Now in this case, ideally we can skip this condition because q is never going to be empty. So even if we say if n is, while n is not equal to 0, keep doing this. Every time we are printing, we are subtracting n. Okay, so this way we can print the binary counting. So the question is, how is q helping here?
Every time we are removing from the front.
Every time we are removing the front of the queue. After removing the front, we want to put its neighbors, but we want to put next values after the other values, right? So that is the property of queue and that is what we have used here. Now same fact is also used in trees. Let's say there is a tree 2, 3, 4, 5, 6, 7. There is a special traversal in tree which is called level order traversal. What does level order traversal mean?
Traversing level.
Level by level. What is the first level? This. Second level is this. Third level is this. So output of level order traversal for this tree will be, can you tell what is the output? 2, 3, 4, 5, 6, 7, correct? Now if we have to do this traversal, first we print the root, then we print left child, then we print right child, and then we print children of left child first. Again we can see, like, after printing this we went here, after printing this we went here, and after printing this we again came back to 3 and say 3's children should be printed. Can Q serve this purpose here for level order traversal? How?
First, push the right child, after removing the root, then push the right child and left child.
Why right and left? Q will be first in first out, na?
Yes. Okay, left hand.
Okay, so first what we will do, we will use the similar approach that we used in binary counting. We will first push the queue itself to itself in the queue, right? If root is not null, push 2. Now queue has only 2. We will write a while loop while queue is not empty. What we will do, we will take the first element of the queue out, which is front, and we will print that. So what are we printing? 2. After printing 2, what should we put in the queue?
Left and right child.
Yeah. So after printing, we'll remove it. Its left child is 3, right child is 4.
We are putting in the order in which we want to print it, right? So after 2, 3 should be printed, right? So 3 should go there.
Okay, so this is enqueued now. Next, what we should do in the while loop?
Remove 3 and again push.
Yeah. Take 3, print 3, remove 3. Take 3 is q dot front, print 3 is printf, remove is pop. So 3 is also printed. Now what should we do? After 3 is taken out, its left is 5, right is null. Should we enqueue 5 and null both? We have to check. Before enqueuing, we will check. If it has a left child, only then enqueue. If it has a right child, only then enqueue. So after 4, we will enqueue only 5, nothing else. Right? So 3 is printed. Next 4 will be printed. 4 has 2 children. They will go after 5 in the queue. 6, 7. So queue is helping us maintain the order, that once this is printed, we can't go to its children until all its siblings are done. So siblings are kept in the queue. And after the siblings are done, only then we will process the children. So this is a very important traversal from interview point of view. Nobody asks pre-order, post-order, in-order traversal in interviews, but level order people ask. Then they also ask twisted forms of level order traversal. So first we will do the level order traversal in today's class, and then we will go to twisted form also, and then we will do iterative version of pre-order, in-order, post-order. Recursive is easy to think and to write. We don't even have to think for recursive version, right? We know it by heart. So we will do iterative version. So today's class is mainly focused on traversals. So if you come to class 13, class 10, this is mainly given to traversals. I think ordering will be level order will be down, but we will do a level order first. Yeah, so there is third problem, level order. So let's start with that.
Left and right.
Okay, so what we will do here, just to quickly discuss, there are few problems, few people who are not done. So we say if root is null, what do we want to do in level order traversal? Return, don't do anything, right? And then we take a queue. What do we store in the queue? Node. Why are we storing node? Why not int? What is the reason we are storing node pointer rather than storing the int? Because when we take it out from the queue, we want to access the left and right children. Int will not give left and right children, pointer will give. So here we do q dot push root. So that has been done. And then we say while q empty is not true. Now we want to do 3 steps. First, get front, print front. If front has left child, push in the queue. If front has right child, push in the queue. So these 4 things we have to do. Here what we want to do? So you are printing temp. No. Why are you putting temp in root of it? See the solution there. These steps are clear? Second?
Print front data.
Those steps are clear, what we are showing there. So how do we get the front? Q dot front. What will it return? BST node? B, is it? Or node star? It should return node star because that is what we stored. Now what we do? We have to print this. Print %d b arrow data. Then we say if this has left child, so we say if b left is not null, we say q dot push b arrow left. Same way, if b right is not null, we say q dot push b arrow right. Now if I go and submit this code, it will not work. Can you tell me why it will not work? There is a small mistake in this code. Yeah. If you are not popping, what will be the result? Infinite loop, because Q will never be empty and we will keep on going. In infinite loop, it will keep on printing because every time it enters the loop, we are printing some data. So pop is very important. So where should I do pop? Can I do it here? Or it has to be done after printing? After printing, what is the wrong thing if I pop here? Yeah, but I have its address in my variable B, right? So in B we copied whatever address was stored in the front. Since we have a copy, even if we do pop here, it shouldn't be a problem, right? So this should work.
And that's why in last class I said that in a stack and queue, always write top and pop together. In a special cases, there may be some steps in between, but most of the cases it will be together, right?
So everyone done with this? Pratna? No, you are done? Help her. She's okay, what the next problem is saying is, I'll just draw the tree. 4, 2, 5, 6, 9, and let's say 2 has 3 and 11. If this is our tree, we want to print the nodes level wise. That means first level you print here. When you are printing second level, print that in new line. When you print third level, print 3, 6 and 9 on a separate line. 11 on a new line. That is what the problem statement is saying, on a new line. So this is what we want to achieve. This is again a level order traversal, but there is a small twist given that each level value should be printed on a separate line. How do we achieve that? Any ideas?
We can take count variable, and if it is power of 2, then we can print 2.
Okay, good suggestion. He says take a count variable. If it is power of 2, then do a new line. And that is coming from, like in first level there is one node, second level there are 2 nodes, third level there should have been 4 nodes, but right now there are 3.
But we increment only when it is not null. But we increment count every time.
Okay, we increment count every
We
time.
are checking count because to verify that whether it reaches the next level or not.
Okay, so we still take a queue. Okay, so let's try the approach that Karthik is suggesting. He says take a queue and put 4 in it first. And what will be the count variable right now?
Initially 0.
Initially count will be 0. Okay, so count is initially 0 and we have put 4 here. Now we write a while loop. while q is not empty. Okay, then in the while loop we take the first value out.
Initially
Count is
1.
1. Okay, initially count is 1. Let's take the first value out, which is 4. So we print 4 like we did in level order previously. Okay, after printing, what is it that we do?
We pop it.
We pop it. Fine. So q becomes empty. Then
We NQ left and right child.
NQ left and right child. So we NQ 2 and 5. Okay.
Then we check count. If it's power of 2.
Okay. So 1 is power of 2 because it is 2 to the power 0, and we know how to write that efficient function. It is power of 2. So we are seeing an application here. Okay. So it is a power of 2. So he says after 4 give a new line. Now we are done with one iteration of the loop.
Increment count.
And increment count also. So count becomes 2 now. Okay. Next.
4 to 2.
Let's go to 2. Okay. So we print 2. We NQ its children. Okay. So children is only 3 child. One child it has 3. And what we do count plus plus. Or we check first count is power of 2 or not. Where the check is coming.
So every time we check at the end of the loop.
At the end of. After we have NQ'd. So value of C is 2 right now. Correct? Okay. Which is the power of 2. After processing 2, you have printed 2, you have NQ'd its children, and you are checking if it is a power of 2. Yes, it is a power of 2. It is 2 to the power 1 now. So here what fact you are missing is first level was 2 to the power something. After that in second level, it should become 1 plus the nodes on second level. Only after it becomes 3 you want to give a new line, right? Because this count is not telling number of nodes on one level. This is telling how many you have printed till now. Correct? So till now you have printed only 2. This count is telling you that. So let's go with this. Second level will be done when count becomes 3. Correct? Third level will be done when count becomes 7. So it is 2 to the power something minus 1. Correct? Okay. So after 2 we don't give the new line. We print 5 the same way. We NQ the children of 5, which is 6 and 9. Now C becomes 3. We check that this is 2 to the power something plus 1 or minus 1. This is an odd value, and then we give a new line. Right? Now comes the challenging part. Here you will be printing only 3 nodes. Null is not even coming into the picture. You assumed if null is there, I will still increment the count. You said that, right? But null we are not storing in the queue. So how do we make sure that rather than these 3, if they were 2 only, 3 and 9, then again we are stuck. At this level we are not getting the count of 4. There is no way for us right now to get the count of 4.
First find the height of the tree.
Okay, first find the height of the tree.
So level start from 0, 1, 2, 3. So
Correct.
first level consists of only one node. And second, first level consists of 2 nodes.
First level consists of one node, 2.
0, that is 2 power 0.
Okay.
Next
Then
is 2 power 1.
5, 9, 7, 2. What about this kind of tree?
Means if it is not having, we shouldn't push into it.
If it is not?
If it is null, we shouldn't push.
Yeah, that's true. But how will you tell when level is done? That is the main thing that we are tracking. So you counted the height 0, 1, 2, 3. Height is 3. Now tell.
For every level, I will iterate from 2 power that level times.
Okay. Where will you iterate? You are using a queue, and queue will have some values in it. So initially queue will have 2, then it will have 5 and 9 after 2 is gone. After 5 is gone, it will have 7 and 7. You are at this stage now. Now how do you tell that level has changed? That is the main question we are tracking. How do we tell the level has changed? Any other thoughts, any other ideas?
We use 2 queues, one for
12 plus? Okay, 2n plus 1. Okay. But right now what is n in this tree? 7. Is it 2n plus 1? 2 into 7 plus 1 is 15. Okay, maximum can be 15, okay. 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 Okay.
But when it start putting null also.
Correct.
Only take it.
No, but again the question is at third level you see. Third level there are only two nodes. Your count will not increase more than 2 there. Your count will never increase to 1 plus 2 here.
That will
3 and plus 1.
maintaining the
That is what you are doing, right? Level wise level you are saying how many maximum are there. But third level you print only
null
2.
also.
How will your count variable go and
when you are
cross that value?
pushing the children, nulls children also assume it is null, two nulls, and push them.
Yeah, any other approach that we can use? Only trick we want is when the level has changed. Can we put some flag in the queue in such a way that tells us the level is changing? Think of it. We enqueued 2 in the beginning. After that level change, you know the first value you put in the queue, after that the level has to change for sure. Let's put some flag in the queue. How do we put a flag in the queue? What are we able to store in the queue? We are able to store. What do we store in the queue? The address of any node. So what can act as a flag for us? Null. So let's put 2 and null. So this null, when we take it out from front, null will tell you don't have to print this value. This is just telling you the level is over. Correct? Let's go with that approach and see where we reach. So we put 2 and null in the beginning before we start the while loop. Now you take front out. Front is not null. You will have a check now. Previously we did not have a check. Whatever is coming out, we were printing the value and we were putting its children. So when you take the front value out, you check. If it is not null, what should we do? We should print it fair. Then if its left child is not null, we should put that, and right child is not null, we should push that. In this particular example, what will be there in the queue after 2 is printed and removed? Null, and we have put its children also. Null, 5 and 9. That is what we have right now. Correct? Now, again in the while loop we take the front of it. So front will give us something which is null. What is the null indicating?
New line.
The level is over, print a new line. And after null, what should we enqueue back? If first level is over, that means all its children are in the queue. That means second level is also over in the queue. If null you pop out, what you do, you push another null in the queue. That will act as the end marker for the second level. And then you give a new line. And you don't enqueue anything apart from null there. Right? Then what will happen? Now null is also taken out. 2 is taken out, null is taken out, you have given a new line. Now let's talk about 5 is coming. So what will we do at 5? So far we have printed 2 and new line, correct? Now we take 5 out. What will we do? Print it, second line 5 is printed. Then after printing we pop it. So from queue 5 will go away. Then it has a left child 7. 7 will be enqueued. 7 will be put in the queue. Correct? Okay. And no, here we will not push any null. If its right child is null, we will not push it. So in the queue, what is there right now is 9, null and 7. Because after 5, 9 we push one null. 9 null and 7 is there. Okay. Now you take the next element out, which is 9. You will print 9 and queue its child again 7. Right? So after taking 9 out, printing 9, you will check there is a null. Next value is null. Null says print new line and insert another null. Because this level is done, all its children are there in the queue. Put another null to mark the end of level. Okay, so now what will queue have? It will have 7, 7 null. Everyone agrees it will have only 7, 7 null? Right? Now first we take 7 out, we put child of 7 which is 2. So Q will have 2 now. We take second 7 out, that will also have 2. So what Q has now? Null 2 2. Both 7s are printed. Believe that I wrote as 2. Yeah. So now Q has null 2 2. After that, when you take null out, what will you do? Print a new line, put a new null in the end. So now Q has null null, sorry 2 2 null. That is what we have. We take 2 out, we print it. 2 does not have left child, does not have right child. Do we NQ anything? No. Now we are going towards making the queue empty. You take the second 2, print it, it does not have left child, right child. You print it. After that you take null out. What do we used to do when we take null out? Print a new line, then we used to NQ. But if we NQ null now, linked list, sorry, queue will always keep on getting null null append. So what should we do? Check if the queue is empty. So when you take something out from the queue, when you pop it, if it is null, before NQing another null, you check. If queue has become empty or break. Because if null comes as the last element, we don't want to continue further. So we want to stop there. So that is the trick that we have to come to. That last null should not make another push of null. So this is the approach. Now we can quickly code it, print it, and see what is the output. Okay, so here if we see, we first check if root is null, what should we do? If our root is null, return. In that case, we always have to remember that we have to handle. Otherwise, we take a queue, bst node star q. We say q dot push root and q dot push null. So this is the pre-handling that we have to do. Then we say while not q is empty, first thing that we used to do was we used to take the element out of the queue. So one way is I can declare a new variable to store this value, or second way is can I use root? Because root is anyways put in the queue, I can use root also as a variable and I can say q dot front. Right? Now there are two possibilities that this thing that we have taken out from the queue, it can be null or it will be not null. So let's first see if root is not null, what should we do? And then else if it is null, what should we do? So what if root is not null? What do we want to do here? We print its value %d root arrow data. Then if root left is not null, we say q dot push root arrow left. If right is not null, if root arrow right is not null, we say q dot push root arrow right. Anything else you want to do in this? Yes, there is something else. Yes, pop. We want to do pop also. We don't want this to be there in the queue anymore. So again I said pop we can do before or after, that doesn't matter. So we are doing it after printing. Now the question is, if this was null, what we should have done? First we have to pop. Yeah. So first we say q dot pop, then if q dot empty, if q has become empty after this pop, we don't want to do anything else. But if q has not become empty, that means we will say q dot push another null and printf a new line. Right? Now in order to submit it, we will have to hash include q, or can I also do, I remove all these hash includes and I say hash include. What is one file if we include? Then all header files are there. Bit std c++.h. This one header file if we include, then we don't have to include individual files. All header files will come automatically. So will this work, this solution, or there is still anything missing? So let's give it a try, submit. So all test cases passed. Everyone is clear why we are doing every line of code that we have written is there for a purpose and why we are putting that? Huh? This if condition. See, imagine if there was last null in the queue. So if your tree is only 1 and 2, let's say this is the tree, right? So first in queue we would have put 1 and null. This is something that we are putting in the beginning, correct? In the while loop, what we do, we take 1 out, we print it, and we also enqueue its left and right child if they are not null. So what do we enqueue in the queue? Only 2. Right is null, so we don't put anything. So 1 is done. Next we get n, null value. So if null value comes, what is it that usually we want to do? We want to give a new line. Done. Second, we also want to put one more n because this n is saying this particular level is over. If this level is over means all its children are also in the queue, because every time we take something we put the children. So that's why we are putting another n to mark end of the second level. Correct? Then we take it out. Both are gone. Now when we take 2 out, we'll print 2 here. It has no children, nothing will get NQ. Now when we take n out, null out, what do we want to do? If we simply put a new line and another null, then linked list, then Q will have another null added. That null will also do the same thing, new line, another null. So that will keep on going. So what we said is when you take this null out, pop it first and check. If this was the last null in the queue, you don't put any other null in the queue. Otherwise it will be infinite loop. So that is what we are doing. In else part, if you see, the first thing that we do is we pop it. So first thing we did is we pop it, then we check if queue is empty, break. This was the last null in the queue. After this there is no other element, so we should not go into infinite loop. If queue is not empty, then yeah, put another null, put another new line, right? And now if you see, pop is there in if condition as well as in else condition. It is there in both parts. So what we can do is we can remove it and we can put it after front. So that way we will save one line of code. That is what sir was mentioning, that every time you do a front, immediately you do a pop so that you don't forget to remove it. So then we don't need this pop here in the second case, else case. Yeah, we can remove this pop from here. So everyone done with this? Everyone clear about this? Is there anyone who needs help who is not yet done? Supriya? Okay. From Gaurav, and this is not giving the right output. We want to see what is the mistake he has made. So let's go line by line and see. So first we are starting if root is null. If root is null, print blank and then come out. That is also fine. Printing blank, okay. Otherwise, what he's doing is he's pushing root, he's pushing temp, because in temp he has already assigned null. So that is fine. We push root and we push null. Now if queue is not empty, we take root is equal to queue dot front and we remove from the queue. If front is temp, what does it mean? If front is null, okay, but now front will not give you null because before this front you have pop. If you pop and check front, then it will give you the next front. Correct? So rather than doing this front, you could have checked if root is equal to temp. Because after popping, the next front will come as answer of front. Understood, Gaurav? What is the mistake? You submitted? Okay, one more submission from Uma Mahesh, and that is saying, Uma Mahesh, where are you enqueuing the null? Before the while loop, where is null enqueued? So if you don't put null, you will never get null out. So in the while loop, null is never going to be there. This condition is never going to execute.
So what is the error here?
It's recording.
Yeah. Root is there, null is there. While queue is not empty, is checking. Now what is the error here? Tell me. If q.front equal to null, then he is doing these things. He is printing new line. He is taking the null out, and if q is not empty, he is pushing the another null. This is okay. In else part, is taking the front that is not null, is printing the data, and is putting left and right if they are existing.
Check the output. He has not given space after the printing.
That is there. But
Okay, it's only coming as root.
root.
Why only root is printing for him is the thing that we have to figure out in the code. Yeah, he didn't push. After if temp left, you are saying temp left.
And this compiled, right? If temp
These are the things that we say you check with your neighbors because these kind of mistakes can be easily caught. Yeah, you're saying something.
this is not a compilation error, right?
Yeah. So what is it that was going on? If temp is null, temp left is not null, temp in front of me. So the person said, what is your rank in the class? I said third. He said, why not first or second? And how do you answer that question? Yeah. Anyone? Or we may be fifth, we may be 10th. And the interviewer asks why you are 10th in the class, why not first? So what is the answer we can give? Boy, okay, who is in this room, who is ranked below 10 in the class? Okay, Vishnu. 10. Okay, Vishnu, if somebody asks you this question, why your rank is so low? I'm sure your 10th marks and 12th marks will be above 90, right? That's norm. I have seen here resumes. Yeah, you are very good in 10th and 12th, and in graduation, this is what happened to you. Why? Then we will share. There is some concept. If we some way of thinking, if you apply that and answer, it will be a good answer. Yeah. So what will be your answer?
10th and 12th constraint. We have to study.
Okay, in graduation, the problem that we have in this class is spiral order traversal. Now, what is spiral order? This says first level you go left to right. It is level order only. Then you go right to left. Then you go left to right. Then you go right to left. So your output will be 5, 12, 2, minus 4, 3, 9, 21, and 25, 19. Understanding, right? First we are going this way to this way. Then we are coming reverse way. Then left to right, then right to left. Alternate level you are going in reverse direction. That is spiral level order in spiral way. Very important interview question. Amazon, Google, Microsoft. Name a company. This question is asked by a lot of companies. And you can build on whatever we have learned in first two problems. And you may also apply stack. We are not going to discuss the solution of this problem today. We want to give you time because this is a question that you may get in your interview. So we want you people to think about it on your own. Try it. Tomorrow we will discuss the solution like we did for binary counting. That was important question. This is also important question. So problem statement everyone is clear about, right? What we have to print and what output should come. And output should be in the same line. We don't want to print output in the separate lines based on the level. It should be one line, 5, 12, 2, minus 4, 3, 9, 21, 25, 19. Okay, so we are skipping this problem so that we give time to you, and we will do the first two, last two.
But just thinking, how do we print the reverse of something? Stack.
So one level, take out and print. Second level, take it out, don't print, put it in the stack till the level is over. When the level is over, print the entire stack. That is one way of doing it. But there are many ways of solving the problem. Even after solving it, you can search online. You should know at least 3 to 4 solutions to this problem. Because sometimes interviewer may restrict you that you are not allowed to use stack. Then how will you do? Right? Or he may say use 2 stacks and do, use 2 queues and do. So interviewer gives some restrictions for this problem. So make sure like what are the tricks involved in solving this? We are mastering the trick. It's not that we have to memorize 4 solutions and say okay now I know this problem. Because they may give a twisted version of this. So learning what you learn by solving this problem is important. Right? That's why we are not giving a solution. Because ultimately that you will say is the best solution, let's stick to that. Okay, so we will skip this problem and we will discuss it tomorrow. Next is pre-order traversal, and the reason we have kept it here is we want to discuss the iterative solution, not the recursive one. So how do we print a tree in pre-order fashion with iterative approach? That means we are writing loops, we are not writing recursion. Yeah, any ideas? In pre-order of this tree, what is it that we want to print? Pre-order of this tree that you are seeing, what will be the output? 5, 2, minus 4, then 3, 12, 9, 21, 19, 25. This is the pre-order traversal. If we have to do that by writing a loop, what should be the approach? See, first thing is very clear, we want to come down this path. Right? So can we print just the left path by writing a loop? Is it possible for us to print only 5, 2 and minus 4? Let's make this problem small and say we just want to print the left side of the tree from top to down. How will we do that? We write a while loop, while root arrow left is not equal to null, print root data and root is equal to root left. So we said while root arrow left is not null, print root arrow data, root is equal to root left. If you do that, what will be the output for this tree? I'm sure it will be 5 and 2, not minus 4. Because for minus 4, root arrow left is null. And you said while this is not null. So for minus 4, it will never enter the loop. While root not null. Correct? Because you want minus 4 also to be considered. So this we can print. Correct? And there are interview questions based on these things also. They say print the circumference of the tree. When you say circumference means print the left side, print all the leaves and print the right side in reverse order. Circumference is 5, 2, minus 4, 3, 9, 19, 25, 21, 12. Circumference is just print the outer nodes. So those kind of problems will also come. Fine, so we have discussed how to print 5, 2, minus 4. correct? But in our problem, when we are doing pre-order, after -4 is printed, we also want to jump to right side of 2, correct? Once left is done, we want to go to the right side. So what data structure will help us, in which we store these nodes when we were coming down? We store so that we can go back to the parent queue. So we put 5, 2 and -4 in the queue. After printing -4, what will come out from the queue? 5. We don't want 5. So stack. So we take a stack, we put 5 in the stack and we print 5. We put 2 in the stack, we print 2. We put -4 also on the stack and we print -4. Now root has become null. So while loop got over, but after this while loop is over, stack has some values in it. Correct? Okay. Next what we should do? We should take -4 out. Right? And since we put these values on the stack after printing them, we know if we take them out, we don't have to print them. Correct? So if -4 has come out, what is the next thing we should do for -4?
Push it right.
We should go to its right child. But right now we see its right is not there. So if it is right is not there, we don't push into the stack. We come out from there. Right? And next what we should do? 4 is gone from the stack now. What is stack having? 2 and 5. So next we take 2 out of the stack and we see if it has a right child, we push right child on the stack. So what will go on top of stack? 3. What is before 3?
5.
Before 3 there was 5. So you take 3 out. 3 does not have a right child. But one more thing here. Okay, first condition is always if root is null, return. Or we can say if root is not null, then we want to do the processing. So first print node and keep going left. This is what we want to do. So we can simply say while root not equal to null, or while root, we say root equals root arrow left. And before that we print also %d root arrow data. This is what we discussed. But we said while coming back we need them on a stack also. So what we do, before this we declare a stack, we create a stack bst node star s. So we ensure stack should be included, hash include stack. Now when we are going left, we should do s dot push root. This is clear why we are pushing on the stack. Now question is, once we come out of the stack, what do we want to do? Sorry, once we come out of the while loop, root would have become null. We want to still do some processing, right? So this was only for every node to go to the left. So outside we need one more loop. So I'll write while true. So I want one loop outside. We will figure out when we should break it. That we will figure out later. So first we say, first we are keep going on the left side, we keep printing. That's it, we have done. Right? After we have come out here, what is the next thing that should happen? If we are out of the first loop, what should happen? We should pop, right? So can I say root is equal to s dot top and s dot pop? We can use root itself because root became null earlier and everything is there on the stack. Now root will be pointing to the previous node that we pushed into the stack. We can push pop before assigning to root. If you pop before, then top will give you the second value. If stack has 1, 2, 3, if you pop 3 will go. Now you do top, 2 will come. We don't want to. 3 has no left child. But it may have right child. Right? We can't ignore that fact. It may not have a left child because if you have a tree like this, 1, 2, 5, 9. So reason we are pushing them on stack is even if it does not have a left child, it may have a right child. So we can't ignore that fact, right? So now when we said print 1, print 2, then we reached null here. Stack has 2 on the top, 1 previous. Now we are at this stage, 1 and 2 have been printed. This is stack. What we do, we take the top item of the stack. Once we have taken 2, what we want to do is we want to move to 5 and say do the same thing that we did with 1, because 5 may also have a left child. So whatever we did with 1, we want to repeat with 5 again. So what we will do for that is we will say if root has a right child, what we want to do, let's move root there and let the first loop take care of it. The first loop will again start from printing it, going to the left of it. That is what will happen, right? So this looks like it should work, but there may be some issues if you try this approach. So just try coding it, submitting it, and see if you get into any issues. Yeah, while true will never come out of the loop. So that is the thing we have to figure out. When should we break the loop? When stack is empty. Where to put that condition is something that we are leaving up to you to figure out. So this is the idea. What we want to do. Fix it, submit it, and see if it works for you. Sahiti, we are stopping here. Do you have any questions? Okay, then see you tomorrow.